When within statistics we're looking to come up with a probability of a certain outcome occurring within a given presented scenario, we can employ something called the binomial distribution. And this is a method whereby we can take the details of the scenario and structure it in such a way that we can make an equation which will give us, say, the probability of any given outcome happening. There is another type of distribution within statistics, which is the normal distribution, but that will be dealt with in another video. Here, we can employ the binomial distribution if the scenario the question gives us meets three criteria. There has to be a fixed number of trials, so you don't just change partway through how many times you're going to do it in total. There needs to be a fixed probability, or in other words, the trials are independent, so the result of one event doesn't impact the result of any subsequent events, and that there are only two possible outcomes, like you either succeed or you fail. You get either heads or tails when flipping a coin. If the scenario does fit this criteria, then we can create a model as such, so X, symbol B, N, P. What these each mean is X is then the variable that you are looking to study. This squiggly symbol here, that is just saying is distributed. And then the B is to say binomially. So this is just confirming for us which distribution we're going to be using. Then here within the bracket, the N stands for the number of trials, and the P is the probability of success. So what are the chances that each individual scenario is going to come out the way that you want, that you have defined as successful? So you just read through your scenario and just like, okay, what are the number of trials? What is the probability of success? And then what exactly are we looking for in the scenario in terms of our X? Are we looking for like, what's the probability that X is an exact value, is specifically 3, is 4? If it's like X equals X, well, to be clear, the variable is capital X, and then the specific value from the scenario is a curly lowercase x. So the probability of X equals something. When you put this into your calculator, when you go into the distribution section, you're going to want to select binomial PD. Yeah, to be clear, when we're getting into this area of statistics especially, you are going to want to have an advanced enough calculator that has specific distribution functions. So yeah, so if it equals something, you'll use binomial PD. If, however, it's an inequality, let's say at most 3, at most 4, or at least, or less than, something like that, you'll be using CD, which is your cumulative distribution. Now, to be clear, when you put this into your calculator for the binomial, your calculator will automatically do this. So probably your variable is less than or equal to whatever number you put into it. In the event, though, that your question isn't using this inequality sign, it's using one of these other ones, we'll have to work out how to change this so that your calculator can work it out. So, for instance, if you had the probability is just less than X, in terms of what you're going to put in your calculator, you'll need to treat it as less than or equal to X minus 1. Because these X is relating to out of the N, out of the number of trials, the number of times this has succeeded, X has to be an integer, has to be a whole number. You can't have succeeded 1.5 times. You either succeed once or twice. So to get to the next one below, you're minus 1. So just as an example of that, if the question was asking you to work out that, that would be the same as less than or equal to 2. So 2 is what you would put into your calculator. If the question instead is saying greater than or equal to, what you're going to do is 1 minus, because the probabilities all added up are going to have to equal 1, because that's a certainty. So if you take away from 1 the opposite probability, that leaves you with this one. So 1 minus probability that X is less than or equal to X minus 1. So let's just say that this had been a greater than or equal to. This then beneath would have been 1 minus probability probability of x being less than or equal to 2. Lastly then, if it had just been x is greater than x, so in this case 3, you would have had here less than or equal to 3 again. Hopefully as we go through the questions it will kind of make sense as to which one you're going to be using where. Speaking of questions then, let's look at an example. It's claimed 40% of diners choose organic food. On a random day there are 20 diners. Suggest a model to describe the number x of diners who eat organic, and then find the probability that this x is greater than 5 but less than 15. Well, to start off with, the first part, suggest a model. This is what we've meant by the model. So x, we're going to say, is going to be distributed binomially, and we'll determine this if it's not explicitly a binomial paper, so i.e. your exam, because in this case there's only two possible outcomes. You either eat organic or you don't eat organic, and presumably the act of one person eating organic isn't going to impact a subsequent diner who comes in later. So x is distributed binomially, and our n is the 20. It's a fixed 20. We know there are 20 diners who are going to come in this day. And then for our probability, we just want to express this as a decimal. So 40% as a decimal is 0.4. Okay, that's our model. And then for finding this here, well, how we can think of this is if we were to work out the probability of x just being less than 15 in general, and then take away from this what would remove all of the lower numbers that we don't want. Now, to be clear, obviously we want to be less than 15. Here though, we don't want to include the 5. We want any number that's 5 or less we're going to get rid of. So here we're going to take away the probability that x is less than or equal to 5. So that A takes care of the 5 that we don't want, leaves us what's above, but also it's already in this less than or equal to form that we want. With that in mind, we're actually going to just change this here, because being less than 15 from this here is going to be the same as less than or equal to 14. So now that you have two probabilities that are in the right format, that are in the form of less than or equal to, you can plug numbers into the 3 sections in your calculator. When we're going into the binomial CD, because it's inequalities, you'll have an option to put in your x. For the first example, x is going to be 14, n is going to be that 20, and the p is going to be 0.4. That should get you a probability of 0.9984. And if you do the same again, it's just this is now going to be 5. That gets you 0.1256. So minusing them from each other, you end up with a probability of x being between 5 and 15 of 0.8728. If we're okay with that, and you're happy with how going through this question we've picked out the relevant n, p, and x values, how we determined what is it PD or CD, and what numbers we put into the calculator and so forth. Let's see how you can get along on a question of your own. So the probability of an egg having a double yolk is 0.05. Eggs are sold in boxes of 12. If 3 boxes are bought, what's the probability that exactly 2 of the boxes contain exactly 1 double yolk egg? Read it through, think exactly what kind of model you're going to be using at each stage, what numbers go where. Pause the video, have a go for yourself, and then press play again when you're ready to compare. So, to start off with, we need to work out what the probability of an individual box having exactly 1 double yolk egg in it. To make our model, you'll have x is being distributed binomially because it either does have a double yolk egg, or it doesn't. And then your n within an individual box, your n is 12, and the probability of it having a double yolk is 0.05. in this case, because we're looking at it being exactly 1, it's the probability that x equals 1, so you'll be using binomial PD in your calculator. Still, you're going to have your spaces for x, n, and p. So you put x is 1, n is 12, p is 0.05. That should get you a probability of 0.3412. So this is the odds that an individual box has exactly one double yolk egg in it. So all the other probabilities cover it either having no double yolk eggs or more than one, so 2 through 12. Now that we know this, we're actually going to move on to another second model to work out the probabilities for the boxes. So now we're going to say the distributed binomially again, and then n is 3, because there's only 3 boxes. And the probability of an individual box having a double yolk egg is this probability we just worked out here. So the 0.3412. Here, we're now after the probability that x equals 2, that 2 of these 3 have that. And so once again, because it's equal, we're going to be in PD. You say stay in the PD section of your calculator, put in now x is 2, n is 3, p is 0.3412, and putting that all in, you should have a probability of approximately 0.23, that 2 of the boxes contained each exactly 1 double yolk egg. Good with that, let's just round off by looking at an exam question. So this one is a bit longer, and not all of it is actually binomial, but I want to include all of it here anyway, just to show that the questions can kind of shift concept partway through, and how you're supposed to spot this and how you deal with it. So, in an experiment, a group of children each repeatedly throw a dart at a target. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. Peter models h as binomially, with n being 10 and p being 0.1. State 2 assumptions Peter needs to make to use her model. Now, if we think back to the criteria that a binomial scenario has to fill, she's not going to be assuming that it's a fixed number of trials, because she knows that. She has set the situation up that it's 10. And similarly, it's not an assumption that there's only 2 outcomes. You either hit or you don't. So for the 2 assumptions left, what we've got is a fixed probability, and that each trial is independent. Okay, so that each time is an equal probability, and that the chance of one person hitting a dart isn't impacted by whether they've hit the target with a dart previously. Yes, these 2 concepts are interlinked, but they are being treated as 2 separate assumptions in this question. Well, then using Peter's model, find the probability that h is greater than or equal to 4. Well, from what we had above, if you have a greater than or equal to, that's going to be the same as 1 minus the probability that h is less than or equal to the number below, which was 3, because we want to get rid of everything that's below the 4, so 3 and below, in order to leave us with 4 and above. So before we know that our n is 10, the x from here is going to be 3, and our p is 0.1. So if you plug that into your calculator, you should get a probability of 0.0128. So let's say go 4 decimal places. Now then, if we read on, for each child, the random variable f represents the number of the throw on which the dart first hits the target. Using Peter's assumption about this experiment, find the probability that f equals 5. Now, this is no longer a binomial distribution because there is no fixed value of n. Up until 10 throws, presumably because that's still the scenario we're going with, they're just going to keep on throwing the dart until they hit. And once you have hit the target, you're done in regards to this probability, because it doesn't matter how many times you hit afterwards. You just want to know what's the probability, in this case, that the first dart that you hit is the fourth, or is the fifth one. So we're going to treat this slightly differently. Here what we're going to say is that if you're going to hit this dart on the fifth attempt, then you need to have failed the first 4 times. So if the probability of success is 0.1, the probability of failure is 0.9, because again, probabilities need to add up to 1. So failing 4 times, 0.9 to the power of 4, then you succeed, you do hit on the fifth go. You just plug this into your calculator and you end up with 0.0656. The reason why, if you at all know about the general binomial expansion, where you would usually precede this with an NCR, the reason why we don't have to do this here is because that then looks at the probabilities of any combination of these. If we did an NCR here, that would also do like, okay, you hit on the third one and then fail it afterwards. No, we specifically in this case have to have it this way round. You specifically have to fail 4 times, then succeed on the fifth. So there's no other permutations. This is the only way the model works. This is all you need to do. Thomas then assumes that in this experiment no child will need more than 10 throws, so there we go, 10 again, for the dart to hit the target for the first time. He models the probability that f equals n, where n is going to be the number of times it takes to hit, as 0.01 plus n minus 1 times a, where a is a constant. And we need to find this value of a, or alpha. To begin with, because this is just a regular distribution, it's not binomial, we would have to just work all of this out. You'd have to go, well, the probability of f equaling 1, because we can't start with 0 because you can't have hit without throwing. You'd say, okay, that's going to be 0.01 plus 1 minus 1 alpha, which is going to be just 0.01 because 1 minus 1 is 0, 0 times alpha is 0. Probability that f is 2, you get 0.01 plus 2 minus 1 alpha, so you end up with 0.01 plus alpha. And I'm just going to do one more to prove my point. So probability that f is 3, 0.01 plus 3 minus 1 alpha is 0.01 plus 2 alpha. Now, we can just quickly write through all the way down to f equals 10. But if we may notice, if we just look at the answers, each time you always have this 0.01, it's fixed, right? So if we're doing 10 terms, you are going to have 10 times of this 0.01 if we're going to add them up. And yeah, to be clear, at the end, what we're going to do is going to add them up because we know that the sum of all the probabilities has to be 1. So add them all up equal 1. So we're going to have 10 lots of this. And then after this, we're going to have, so 1 plus 2 plus, and all the way up to 9 lots of alpha. I was not going to go up to 10 because in each case, the number of alphas in the given equation is 1 less than the value of n. So starting at 0, so 1 add 2, blah, blah, blah. This gives us 0.1 add 45 alpha. As I say, because this is all the possible probabilities there can be, we can't have f being, or n being 0. You can't have it being a decimal because you can't have like a 1.5 throw. And the question is saying we can't go beyond 10. This is all the outcomes. Add them together. They must equal 1. So now just rearranging. 45 alpha equals 1 minus 0.1, which is 0.9. So alpha will be 0.9 divided by 45, and that's going to give you a value of 0.02 in every case. Now then, given that we know that alpha is 0.02, use Thomas's model to find the probability that f equals 5. Well, if we know here, so probability f equals 5, we're going to have 0.01 plus 5 minus 1 times this 0.02. So you're going to have 0.01 add 4 times 0.02, which is going to be 0.01, add 0.08. So put that together is 0.09. Finally, explain how Peters and Thomas's models differ in describing the probability that the dart hits the target in this experiment. In Peters' model, at the beginning, we're assuming that there is a constant probability and a binomial distribution. However, in this case, in Thomas's model, the probability changes each time. It's not a constant probability, but each time after every throw, the probability that you hit the target increases slightly.